Hello and welcome to the first module of lecture 3 in the course EE302. So the agenda for today's lecture would be, we will see how to model mechanical systems which have translational dynamics as well as rotational dynamics, and we'll also see the analogy between these systems and the electrical systems, the circuits that we've considered thus far. So let me stop sharing the video and resume. Okay. Right, but before we get into this, there's just a small point that I wanted to clarify, uh, taking a relook at what we've done with circuits. All right. Okay. So remember that I told you when you have an inductor such as this, yeah, you can replace this with just SL. All right. When you have a capacitor such as this, you can replace this with 1 over SC. And of course, the resistance remains the same. Yeah, and then instead of dealing with differential equations in this domain, so you have ODEs in this domain. In this domain, they turn out to be algebraic equations. However, there's a small caveat here that I would like to add, which is as follows. Now, these substitutions are only good enough. These substitutions are only good enough if you are considering the problem of finding the transfer function. Okay. But if you're actually looking to solve for the differential equation with non-zero initial conditions in place, all right, then it turns out that just by substituting an L with an SL here, or replacing an L with an SL here, does not suffice. What you then need to remember is the governing equation, which is the voltage across the inductor is nothing but L times DIL dt, which in the Laplace domain would give you VLS is equal to SLILS minus LI. Sorry, this should be small I. This is the time domain, right? Yeah, minus LIL 0 minus, right? And by the same token, when you have the capacitor, you know that the current through the capacitor is given by, I'm dropping the T for brevity, C dVc dt. So in the transform domain, you have ICS is equal to CS VCS minus C VC 0 minus. So what this essentially means is that if you want to actually solve the overall differential equation, then this is how you must replace the L. So if this is the actual L for which the differential equation is written, right? Then you must replace this in the transform domain. That this is the direction of flow of the current. So therefore, this is the plus terminal and this is the minus terminal. And additionally, you must have a voltage source, okay? And remember that the polarity of the voltage source must be opposite. So, yeah. So the polarity should be opposite, and therefore, what you have here is yeah. So what you'll then have here is an inductor followed by a voltage source which has the opposite polarity, and the voltage is given by L IL 0 minus. Okay. So this is required if you are actually looking to solve the circuit, solve for the expression or for the variables in the circuit, all right? Not just obtain a transfer function, okay? And similarly, for the capacitor, if this is the plus and the minus terminal for the capacitor, then if you take again this to be the direction of flow of the current, all right? Then again you consider, but this time with the same polarity as in this, okay? And the voltage source will then have excuse me, the voltage source will then have 0 minus upon S. Okay, so this is the exact replacement in the transform domain that will help you in solving. So we'll have some exercises right at the end of probably this module, or maybe at the end of the lecture. It will come with your slides, so do practice them. Okay, so that's a quick point that I wanted to clarify. Okay, all right, so now moving on to the agenda of today's lecture, and specifically this module. Okay, so let us look at a typical mechanical system such as this, which comprises a mass, right, on which a force is applied. Okay, and this is connected through a spring having a spring constant K and a dashpot. Okay, so let's call this B. Okay, so we know that the forces, if you want to draw the free body diagram for this is what we do. Okay, in the x direction, if you want to draw the free body diagram, so of course this is going to be your f of t, and this is going to be the direction, so the displacement is x of t. Later on we shall drop this t for brevity, and the upper lowercase letters will denote the variables in the time domain in general. Okay, then this is nothing but k times x, and this dashpot, yeah, the force is proportional to the velocity, so it is bx dot. Okay, additionally, if you want to take this to static equilibrium, you apply D'Alembert's principle of pseudo force. Okay, so this has mx double dot. So therefore we can write this differential equation as mx double dot plus bx dot plus kx on one side, which is balanced by the applied force on the other side. Of course, as before, assuming zero initial conditions and taking the Laplace transform on both sides, we may write this as ms squared plus bs plus k times x of s is equal to f of s. All right. A moment's thought would immediately lead you to conclude that this looks uncannily similar to an expression we've already encountered before. What is that expression? ms plus b plus k over s times sxs is equal to f of s. What is this? This is the Laplace transform of velocity, is it not? The derivative of the position, right? It's a small s. So s times xs is nothing but the velocity in a transform domain, all right? And this looks very similar to the usual equation that we write in an RLC circuit. This is the L, this is the R. Just to refresh your memory, we've done this already. And this is the voltage source, all right? This is the VT. So exactly in the same fashion as we wrote the equation for this, if I now write a one-to-one correspondence, you shall see that, you shall be immediately able to see that this looks like LS plus R plus 1 by SC times IS is equal to V of S. Okay, so you see the immediate analogy here, right? The analogy is between the force and the voltage, the velocity and the current. Okay, so the K is equivalent to 1 over C, that's the spring. Okay, just that you have to remember the relation. The R is equivalent to the damping coefficient, and the inductor is equivalent to the mass. All right, so this is an equivalent, one-to-one equivalence. You can also say that basically the displacement is the equivalent of the charge. Yeah, you can immediately see that that is indeed the case. Okay, so this is the series equivalent is what we call this. Okay, the series analog, the series analogy. All right. So let us quickly take an example of a system. We'll take right away a system which has multiple masses, multiple bodies, okay? And we'll see that exactly in the same spirit and in the same fashion that we had considered, okay, it's all about remembering your free body diagrams that you were accustomed to drawing when you solve problems on mechanics. Okay, yeah. So let's say this is like a box which weighs 1 kilo, 1 kg. Okay, so this is M2, so this has a displacement x2, all right? And here is another mass that is sitting inside this box. Okay, this is M1 is equal to also 1 kg, and a force is applied to this, all right? So this is where the force is applied, and of course this is tied to this through a spring of spring constant. So later on we shall drop these units, just the numerical values would suffice. For now I'm just retaining them, all right? Yeah, and this is a dashpot here, right, which also has a magnitude. So let's call this B3. It'll be clear why I'm calling this B3, Newton second per meter, because there'll be other factors that can be called as B1 and B2. So the displacement of this, the displacement of the big box inside which everything lies, yeah, that is given as x2, all right? So this is x2, but the displacement of the smaller mass inside this box is known as x1, all right? Also, apart from this dashpot, there is a coefficient of friction here, which behaves in much the same way as the dashpot does, all right? So this B2, this also has a magnitude of 1 Newton a second per meter, all right? So there's a B here, and also there's a B here, which we call as B1, that is also 1 Newton. So these two surfaces both have the same kind of friction, all right? Additionally, this entire setup is resting on this surface, which also has the same damping coefficient, which is 1 Newton second per meter. The point is, how do you write the equations at one go? So of course, let us take this one by one, bit by bit at a time. Later on, when you see the analogy more obviously, then you will be able to see that there is a straightforward way of writing this, just like you could write the equations of KVL in a straightforward way. All right. So what is this? This is nothing but K times x1 minus x2, right? Because this fellow moves x1 to the right, but this fellow moves x2 to the right. So the net movement is x1 minus x2. The net compression or elongation of the spring is x1 minus x2. Similarly, this is B3 times x1 dot minus x2 dot. All right. So similarly here also, yeah. Yeah. So in this surface also, you have this force that is applied. So we are assuming that, well, let's say we reverse the arrowheads here, right? Because we are pushing in this direction. So it is to be counterbalanced. Yeah, because these are going to be opposing the motion. So if we are pushing in this direction, this is the direction in which this is being applied. So we are assuming that x1 is towards the right. So these are applied in this direction. All right. Similarly, here also, you see this motion x1. So both these B2 and B1, they also apply forces that are proportional to Here B1 x1 dot minus x2 dot. Here it's B2 x1 dot minus x2 dot. And then you apply the pseudo force, right? Yeah, you apply the pseudo force in the opposite direction of the actual motion. So that is m x1 double dot. So clearly now equating all of these, the forces to the left and the forces to the right along the x direction, we can write out the equation as f of t is equal to m x1 double dot plus 3b. Actually, these b1, b2, b3 are just unity, so I'll just write them as 3. In fact, I'll just drop these symbols now because mass is also unity, right? Okay, so this just becomes s squared x1 s plus, so there are 3 coefficients there, b1, b3 and b2, right? So that is 3 x1 s, 3s times x1s, and there's one spring here involved with it, so that is x1s. Rest of it all will come as minus. So what is the minus? What is the equation here? So you see all of these involved x2 term in terms of so far as the damping is concerned. So this is going to be 3s x2s, right? And also there will be another resultant for the spring. Yeah. So this is going to be, okay, this looks like a hybrid sort of a notation. So let me just write it straight away. So this is going to be f of s. Okay, this is the first equation. For the second equation, you have to draw the free body diagram of the second body, and I leave it to you as an exercise, and you will see immediately that I don't even need to draw the free body diagram now. Having followed this and also following in the same spirit as we did the KVL, applied the KVL to electrical circuits, I can now write, so remember that the force is applied to mass 1, so the net force applied to mass 2 is 0. All right. So what are the additional forces acting on mass 2 now? Even without drawing this free body diagram, I can see that all these forces are acting equally in an opposite direction for mass 2, right? So I can straight away write for mass 2, let me write s squared plus 3s, yeah, plus 1 into x2s. These are just with the same forces acting here, but with opposite signs. So here they appear with a negative sign before x2, here they'll appear with a positive sign before x2. And for x1, there is this 3s plus 1 times x1s. But what am I missing? Remember that there is this additional fellow here, which is only acting on m2, not on m1, right? So there will also have to be, that will also have to be accounted for. So this also gets added. All right. So solving for these two equations, again, I leave it to you as an exercise to check that if you solve for these two equations, what you will eventually get. So I didn't write the goal. The goal was to obtain, let's say, x2s over f of s. All right. This was the transfer function that we were required to obtain. So I leave it to you as an exercise to check that this leads to the following transfer function, 3s plus 1. Again, using Cramer's rule. You have two equations, use Cramer's rule, and you'll find that this leads to s to the power 4 plus 7s cubed plus 5s squared plus s. Okay, so that is the resultant transfer function. You can check, all right? So I hope that you see the analogy, the analogous way in which we can write out these equations. Once you have gained sufficient practice with this sort of problem, yeah, you can actually write this down very easily. But it is advisable to start off with drawing those free body diagrams for your convenience. All right. Now, I will talk about something interesting which is to draw the equivalent circuit for this mechanical system. Equivalent circuit, okay. So first, what I'm going to discuss is something that I'm going to call a series equivalence. Okay, what do I mean by a series equivalence? Notice carefully in this equation here, in this particular slide, you get a one-on-one correspondence between these fellows, all right? So the mass is replaced by an inductor of equal value, the resistance is replaced by a damper, or rather the damper is replaced by a resistance of equal value. Capacitance replaces the spring constant but with a reciprocal, all right? So that is how we can straight away draw this circuit here. So now I urge you to look at this particular equation, the form of this equation. The coefficient of x1 is s square plus 3s plus 1 here, and that of x2 is minus of 3s plus 1. All right? What does that tell you? So let me try to draw the electrical equivalent of this. Okay? So let's say this is the applied voltage here. All right? Okay. Yeah. So what is common to the two loops? If I'm applying KVL, what is common to the two loops? The common part is 3s plus 1. So what does 3s plus 1 manifest itself as? All right. Remember, what 3s plus 1 will manifest itself as is, once we have taken the velocity, look, here we are considering the positions. So if you're considering the velocity, then the 3s plus 1 term, the 3s will correspond to the resistance and the 1 will correspond to the capacitance. All right. So remembering that, we leave this part empty for the time being. So clearly there will be two loops. In the first loop, there will be a current, which is going to be given by x1s. All right. And we draw this capacitance. So since the mass is 1, the reciprocal is also 1. So this will be a 1 farad capacitance. And then we have a 3 ohm resistor. Okay, so this will actually give you 3s plus 1. All right. Okay, what to put here? Now look at this equation here. 3s plus 1 is already appearing here in this. Additionally, you have s squared, which is corresponding to the mass. All right. So therefore, you have to have an inductor of 1 Henry. Yeah, because the mass is 1 kg. All right. And similarly here, what you additionally have is basically an inductor that is M2. Okay, apart from the common part, look at this equation here. Apart from the common part, which is 3s plus 1, you have s squared and you have an s. What does that s correspond to? As we've already seen that this s will correspond to a resistor here, according to our notation. Okay. So this will be again a 1 ohm resistance. And you call this as your x2 over s. So if you write down this equation of this circuit, you'll get exactly the same equation that you obtained here. All right. In that sense, these two are equivalent systems. Okay. Why do I call it a series equivalent? That will be clear in a moment. Now notice that this equivalence has been drawn by just looking at the corresponding differential equation. This is not always the best analog because this actually some insight is lost through this analog. What is that insight? If you remember, in a circuit, in an electrical circuit, current is a through variable. That is, current flows through the elements. And voltage is an across element. Okay. So let me motivate that discussion here. This is going to be the parallel equivalence. Okay. So here we talk about what are through variables. with inputs through variables and across variables. So if you look at it from this perspective, you'll see that the current is a through variable, as is the force, as is a torque that is applied to a body, right? On the other hand, the voltage is an across variable, as is the displacement or the angular displacement in a rotational system. Okay, so these are across variables and these are through variables. Okay, current, force, torque. So if you are actually drawing an analogy in this fashion, that is the force voltage analogy, okay, you're actually losing out certain physical insights for that particular system. So what could be a better way to retain the physical insight and the physical equivalence of the system? Then you should maintain that one through variable in an electrical system, which is the current, should correspond to a through variable in the mechanical system as well. Yeah. In this spirit, it turns out that if you now take a relook at this equation, right? In an electrical circuit, you will have Is given by, so this is in a, for example, if you have a nodal equation, all right? So let's suppose you are supplying a current Is through a source to a junction here, all right? Then suppose you have an inductor here and you have a capacitor here and you have a resistance here. So how does this begin to make any sense? All right. So suppose these are all grounded. All right. So what is this current going to be equal to? If you are interested in finding the voltage at this junction, all right, then this is how you write them. So this is going to be V of S times divided by 1 over SL. That is this current, right? So this I supplied here is going to outflow through these channels plus V of S times into C times S plus V of S times over R, right? In other words, this gives you an equation that looks like this. If you now compare this, yeah, if you now compare this to the mechanical system that we have derived, you will see that this, sorry, if you now compare this to the mechanical system that we have derived, you will see that the analogs have now changed. How so? How have the analogs changed? You will see that this is now mapping to B. All right. This C, that is going to map to the mass. All right. And this 1 by L, so this 1 by R maps to B, the C maps to M, and this 1 by L, right? This 1 by L will now map to what is called the spring constant or the K. All right. So now, given this sort of an information, again, I leave it to you as an exercise to check that for the system for which we've solved or we've written out these equations here, yeah, the parallel equivalent will look something like this. All right. So let's call this the current source, which is suppose Fs over S. All right. Suppose the voltage at this junction is given by X1 S. All right. Then this is going to be 1 farad capacitance here. All right. There's another junction here whose voltage we call as X2 of S. And between X1 and X2, what they're going to share is basically a resistance of value 1/3 ohms. All right. And an inductance of magnitude 1 Henry. All right. And then there will be this capacitance of 1 farad again here. Remember, the capacitance is now the mass. All right. Just like here, in this case, the inductor was corresponding to the mass. Here, the capacitance is going to correspond to the mass. All right. So check. You should be able to see the analog here. All right. And in addition, you have this resistance, which corresponds to B4. Okay. This B4 that is exclusive to the box. All right. So this is going to be the parallel equivalent of the translational mechanical system that I have just considered in this particular figure. All right. So take your time and just see that you understand each of these analogs and see how these circuits are mapping one from the other. All right. Okay. Good. So now that we've covered this, let me just give you another quick bit of info here, or rather a bit of a trivia here. In most of your examples, okay, in the examples that will be given to you in the book by Norman Nice or in other textbooks also, you will find that most often these springs and dashboards, they appear in parallel, right? All that's pretty fine, right? So this is probably connected to a mass like this, right? Which is some mass like this. Okay. So normally, this is how you're used to seeing them. Now, what if, of course, this is a pathological case and you'll generally not encounter it this way. But what if these blocks happen to be connected in series like so? Okay. It turns out that you can treat this like an equivalent impedance. All that you need to just be mindful of is the through variable and the across variable. So suppose there is a connection like this, a contraption that has been built with a spring and a dashboard. So suppose the spring is displaced by x1 and the dashboard is displaced by x2, right? So because the force is a through variable, here is where the physical insight plays a big role. So because the force is a through variable, you would know that this is kx1, that's equation 1. And you would also know that F is equal to B of x2 dot. So taking the Laplace transforms, you would see that F of S is equal to K of x1s is equal to SB of x2s. All right. Now the total displacement that results due to this application of the force is xs total displacement. Xs is equal to x1 of s plus x2 of s. So substituting these relations here, we can write this as f of s upon k plus f of s upon sb. So therefore, if you now want to find out x of s over f of s, the transfer function for this particular system that we've just cooked up, all right, then you would get this as 1 by k plus 1 by ds. All right. So this is a general setup. Okay. All right. So hopefully now you'll be able to see when these elements are connected in series, as if you remember your physics lessons from your +2 level, you would know that when springs are connected in series, there's an equivalent spring constant. When they're connected in parallel, there's an equivalent spring constant, right? So now you should be able to see that here as well. We basically use the same principle here. And this all the more highlights the analog and the analogy between the electrical circuit and the mechanical circuit and the components. Okay. Okay. All right. So having covered this, it is now time for us to move into rotational systems, rotational dynamics. So here, the main difference will be that instead of a force being applied, what will be applied is a torque. You will still have a spring, which will not be a linear spring, but a torsional spring. You will still have a dashpot, which will resist the rotational motion instead of the translational motion, so that I may write this as where T is suppose the torque applied. So for a component such as this, which is a torsional spring, well, let's say T is applied and results in a rotation of theta, I may write this as K times theta T. Similarly, when I have a rotational dashpot given by this, where a torque is applied, right? The relation is given by, let's say, let's call this spring constant K and this as D to distinguish it from the linear one. Okay, spring constant is still the K. You might use some other symbol, but okay, doesn't matter. But at least to distinguish between the dashpots, let's use D here. So this is D theta dot. All right. Okay. And then, of course, we have, instead of a mass, we have now a moment of inertia for a body, all right, which is J. Okay, so this is some rotational body on a shaft, possibly, where a torque is applied, resulting in a rotation. This will be given by, as you all know, J theta double dot. So in much the same fashion, right, in much the same fashion as we wrote for the translational equivalent, here also for the rotational equivalent, we'll have both series and parallel analogs. So for the series analog, we'll just compare the differential equations and arrive at the series analogs. So for example, such as this, for instance, okay. So let's say you apply a torque here. This has a moment of inertia J, this has damping coefficient B. All right. So then the equation will be T of T is equal to J theta double dot plus B theta dot, again by free body diagram, plus this. So in the transform domain, you will have T of S is equal to J of S squared plus B of S plus K times theta. And by comparison with the electrical system here, the series equivalent would tell you, let me just, again, if you're not convinced, just try to convince yourself, take that as an exercise. Okay, so this is going to be the series equivalent. This J will correspond to the L, the D will, the B, sorry, this is D. I should have written D here, not B. Yeah. All right. This is plus, this is D, this is also D. All right. So this corresponds to what is called the resistance in the electrical circuit, and this will correspond to the reciprocal of the capacitance. All right. So this is the series analog. There are several problems, and we'll also give you some problems at the end of this module or probably the end of this lecture, which you should practice. But there are several worked out examples in the book by Norman Nice. I would insist that you go through them in order to clarify and get more practice with these sort of problems. Now, if you want to get the parallel analogs in the same fashion, all right, the parallel analogs would look something like this. So in this case, the capacitor will replace the J, the moment of inertia. The conductance will replace the damper here, the dashpot, and the reciprocal of the inductance will replace the spring here. So this is the parallel analog. As before, you'll see that the parallel analog preserves this notion of through variables and the across variables. All right, so more physical insights are to be had from a parallel analog. which is what incidentally motivates our need for this parallel analog. Okay, so before closing our discussion on these rotational systems, I'll take up an example, all right, and show you how this is done. Okay, so let's say this is J is, I'm dropping the units, okay, this is kg meter squared, I'm dropping the units for the time being, okay, and suppose there's a torque that is applied here, which results in a rotation theta, okay, in this direction. Now you have this connection. This is a, this is going to be a spring, and this is going to be a dashpot. So again, I'm ignoring the units here. We'll assume that the units are compatible here. All right, so this is also of unit value. This is also of unit value. All right. Okay. And then we have another parallel unit of the same. Okay. And this is connected to the datum. All right. The question here involves that you have to, so we call this rotation theta, to remember that these are not uniformly rotated because theta is not a through variable, it is an across variable. So the net rotation up to this point is not the same as the net rotation up to this point, whereas the net torque applied at every section is the same. All right, so the torque is like the current through variable, whereas the theta 2 here in this case, the theta is basically like the across variable, which is the voltage. All right, so straight away I might, without much thought, write the equation for this first part here. All right, so let me call this as theta 1 here. Let me call this, let me call the rotation of, let's let this remain theta. Okay, so let me call this the amount of rotation of this fellow as theta 1 here. All right, at this point. Okay, so what can we write this as? So if you're drawing the free body diagram for this fellow here, this moment of inertia block here, what you might write is T is equal to S squared, which is corresponding to this, plus S plus 1. So this S is coming due to this, plus 1 times theta 1. But remember, this part is also shared with this theta 2. So therefore, this is minus of S plus 1 theta 2. Okay. Now, if you're breaking the connection here, yeah, if you're breaking the connection here, you have to still replace this torque that you have applied here at this, because the torque is a through variable. It is the same as applied here. Okay. But that effect of the torque is already accounted for within this block. So if you're cutting it off here, the net applied torque at this point is, external applied torque at this point is 0. All right. Just like you have with a force, right? Just like you had in the other case, the force was applied to this. Okay, so when you're drawing the free body diagram, you're freeing it out of all the connections, all connections that are not directly linked to that particular body. Okay, so now let's say you cut it off here. Of course, there is no mass or moment of inertia applied here. So this is going to be balanced by, basically a twist of this is going to be balanced by a twist of this. How so? So once again, if I were to write this for this particular segment here, if I'm to replace this force here, what is this force here? This force is nothing but theta 2 minus theta 1 plus, okay, plus theta 2 dot minus theta 1 dot. Yeah. And in addition, there is a twist here, but there's a torsion here, but that is only of theta 2 on this spring and this dashpot. All right. So you can write that as theta 2 plus theta 2 dot. All right. So this in the transform domain. So this in the transform domain I shall write as 0 is equal to, what does it come out to be? Comes out to be s plus 1 times with a minus sign theta 1 s. Let me just write the s here. Plus 2 times s plus 1 theta 2 s. All right. So this is my equation 2. So now if you want to solve for the expression, so the question was obtain theta 2s over t of s. Okay. Again, I leave it to you as an exercise to check that this turns out to be, this g of s turns out to be 1 over 2s squared plus s plus 1. But there's another way of viewing this, and that is specifically the reason why I chose this particular problem. All right. How so? So now suppose you want to find out the same expression, but without writing these equations, but in a different way. Something very analogous to what you do in circuits, right? By considering series elements and parallel elements to be reduced one by one. So how would you do that? All right. So consider this first block and this second block. All right. So the factor coming from this first block is s plus 1. Yeah. That is the relation between the, if a torque is applied to this, yeah, the angle of rotation, the relation between a torque applied to this unit and the rotation obtained at the end by this unit is this s plus 1, right? That is the relation, or 1 over s plus 1. Similarly, for this block also it is s plus 1. And remember that they're in series. So if they're in series, you remember what we just discussed a while back? Yeah. When they were in series, you could add their sort of admittances, right? So following in the same spirit here, you can now take this equivalence to be s plus 1 into s plus 1 divided by s plus 1 plus s plus 1. So that is the net effect of this entire block. Okay. So when I view this entire block, yeah, the exact equivalent will be this. All right. What is that? That is nothing but s plus 1 over 2. So basically then, I could view this as in this fashion, like a torque being applied here, and the theta, if I want to find out the transfer function here at this point, then I can treat this as a ZS block equal to s plus 1 by 2, in which case this will be the s squared times 1 because the moment of inertia is 1. So in this case, you can write that t is going to be equal to s squared plus s plus 1 over 2 times theta s. All right. That is going to be leading you to conclude that theta of s upon t of s is equal to 2 upon 2s squared plus s plus 1. But we are not done yet. Remember, what we are asked to find is with respect to the variable at this junction, not the end variable, right? So it's like finding the voltage drop across one element when you found out the entire voltage drop. Okay. So how do you do that? What you then resort to is as follows. Notice that because the torque applied across these are identical, right? So you can write that, suppose now you call it remember this theta1 and this theta1 notation will not be the same. This theta1 notation is basically the entire theta here. But now we are going to split up the theta into two parts. So we call this theta2 as before, and we call this theta1 as the rotation by this alone, rather than this entire rotation. Here the theta1 denoted the rotation of this j. Okay, so which is the cumulative effect of both the rotations. Here that is being replaced by theta. So just the subtle difference I want to draw your attention towards. So then you can see that you will have t over s plus 1 is equal to theta 1 and t over s plus 1 is equal to theta 2. All right. And theta is going to be equal to theta 1 plus theta 2. All right. So this is going to be equal to twice theta 2. Right. So now you replace this in this equation and you will get theta 2 upon t is nothing but 1 over 2s squared plus s plus 1, which you might check is the exact same thing that you had obtained by writing out these equations. Okay. So because there was no mass here or no moment of inertia here, we could actually combine these impedances. Okay. And look at it in this perspective. So hopefully this much is clear to you. Before we conclude this particular module, there is something that is very specific and particular to a rotational system, such as, which is the gears. Okay. So this doesn't have a parallel analog in translational systems. So for instance, so we're going to talk about systems with rotational systems having gears. Right. So for instance, consider the system such as this. Okay. So you're applying a torque at this point, okay, which gives you a rotation theta here. Let's call this theta 1. Let's say there is a gear here. Okay, so gears are quite often used, as you might know, to step up or step down the speed and as well as the torque. All right. So this is N1. This is a gear having N1 number of teeth. And this is a gear having, let's say, N2 number of teeth. All right. And then you have an inertia block here, which is, let's say, J. All right. Which in turn is connected like so. All right. So how do we go about this? Yeah. At the very outset, notice that if you are to interlock gears of different number of teeth, at least the size of the teeth must be the same, right? So sizes of the teeth are the same. So if the sizes of the teeth are the same, then the number of teeth in a gear basically is proportional to its circumference, or in other words, it is proportional to its radius, right? So we can say that R1 over R2 is equal to N1 over N2, where R are the radii of the gears. This is first observation. Second observation, if two gears are interlocked, then the total distance traveled in that interlocked position. So for example, if this is a gear and if this is a gear, then the total translational motion that is happening between these two is the same, right? If this is the segment that has been, that is the amount of rotation that has happened here, then this will have a greater amount of rotation here in order to cover the same length of the arc here, right? Which just means that R1 theta 1 is equal to R2 theta 2. All right, second observation. So now, using these two relations, we may now write N1 theta 1 is equal to N2 theta 2. So combining these two relations, we arrive at this third relation. Yeah, because the R are proportional to the, directly proportional to the N. So we're just replacing this here. So this is a relation. Okay, this just comes from the geometry of the motion. The next most important relation is very similar to the transformers equation, like V1 I1 is equal to V2 I2 on the primary and the secondary sides of a transformer respectively, you have, right? In the same fashion, the total power transferred, if it's a lossless gear, yeah, so again, that is an assumption. And the total power transferred is equal to the total power received on the other side. Okay, so this is this relation. So combining 3 and 4, what can we write? We may now write theta 1 over theta 2 is equal to n of 2, n2 of over n1 is equal to T2 upon T1. The most important relation when you're dealing with gears. Yeah, if you remember this and nothing else, you don't need to remember things mechanically in a rote learning fashion. If you remember this and nothing else, you should be able to simply sail through this, whatever we're doing here. Okay. So let's now consider this particular figure that we had here. All right. So if you are now transferring this T from this side, let me just call it T1. Let me just name it T1. So if you're transferring the T1 across this gearbox, this gear mechanism to this side, what will it transform to? Will it not transform to? So if you are reflecting this on this side, it will change to T1 times N2 over N1. Yeah. Because whatever torque was appearing on this side, when that torque is reflected across the gear, because of this relation, right? Because of this relation, the torque T2 is going to be N2 by N1 times T1. So that is the torque applied to this. So now you can forget about this fact that there was a gear here. All right. And you can just apply this equation here. So if I just apply that equation here on this side, quite simply, I would get this T1 times N2 upon N1 is equal to very standard J square plus ds plus K times theta 2. All right. But if the question is to find the relation between T1 and theta 1, right, then I have to again resubstitute theta 2 in terms of theta 1. But here these are coupled by a gear and they follow this relation, right? So the teeth ratio gives you the relation between theta 1 and theta 2 as well. So now I'm going to just write that down as J squared plus ds plus K times theta 1 multiplied by N1 upon N2. So now in one step, if I want to write theta 1 over T1, of course, I'm omitting the S subscript, S arguments for brevity. What you will then get is N2 upon N1 over, N2 upon N1 over divided by N1 upon N2 times J square plus ds plus K. Or if I want to simplify this further, I can write this as J equivalent S squared plus D equivalent S plus K equivalent, where J equivalent is equal to J times N1 by N2 squared, K equivalent is equal to K times N1 by N2 squared, and D equivalent is equal to D times N1 by N2 squared. What that simply means is, if you want to get rid of this gear mechanism in between and want to find out the ratio or the transfer function between the theta obtained at this point on this side of the gear, when a force or when a torque is applied on the same side of the gear, then you have to reflect these quantities to this side. And in order to reflect those quantities on the other side, This is the transformation that you have to make. This is the scaling. So in order to find out the equivalent reflection of these, either you consider the reflection of the torque on one side and then the theta on the other side, and go through all those steps that I've outlined here, or quite simply, you might just consider all of these moment of inertia block, the spring and this dashpot to be reflected on the other side of the gear and ignore the gear altogether. The only thing that you then need to do is adjust them with the scaling factor. Okay, so before we conclude this particular module, the last thing that I'm going to do here is to take up another example of this and to solve it. Okay, you'll have a lot of exercises coming up on this. Do practice them. Okay, so again, I'm dropping the units. Okay, the units of these. So this is moment of inertia, from the way it's been drawn. All right. So let's say there's a torque applied here. Okay, and you have a dashpot here, which also has unit magnitude, and then you have this with 50 teeth. Okay, so this is equal to, let's say, N1, and you have another one here which has a N2 is equal to 100 teeth. Okay, and you have a spring connected here. Of course, these are all rotational springs. This has a value of 4. Okay, the unit will obviously be Newton meter per radian, but again, in the spirit of this problem, I'm just omitting those units, assuming that they're all in the consistent units. Okay, the question here to obtain is, if we are calling this as theta 2, all right, and this as theta 1, the question says that you must obtain theta 2 upon t. All right, so what is the simplest way to do this? The simplest way to do this is first reflect the spring to the other side. See, there's only one element here on this side of the gear, right? So if we reflect this on the other side, we might as well write this equation as s squared times theta 1 plus s times theta 1 plus, when you're reflecting, what is the ratio that needs to be kept in mind? 4 times theta 1, and the ratio is going to be 50 over 100 squared, right? So this is going to give you s squared plus s plus 1 times theta 1 of s. All right, that's what t of s is balanced by. Okay, but we are not done yet, because remember, the relation that you have to ultimately find is the transfer function between theta 2 and t rather than theta 1 and t. So this will only tell you that theta 1 upon t is going to be equal to 1 over s squared plus s plus 1. So how do you obtain this? This is very straightforward now. Now you apply this relation that theta 1 n1 is equal to theta 2 n2. So theta 1 n1 is equal to theta 2 n2, which just tells you that 2 theta 2 is equal to theta 1. All right. This implies that if you can write this as 2 theta 2 upon t is equal to 1 over s squared plus s plus 1, which would then lead you to conclude that theta 2 over t, this transfer function, is given by half upon s squared plus s plus 1. All right. So that is the solution that you're looking for. Okay. So this is another example of a rotational system with gears. So with this, we end module 1 of our third lecture. In module 2, we shall focus our attention on electromechanical systems, particularly a DC motor. Okay, and we shall see how speed of a DC motor can be controlled by 2 modes. One is through armature control, and the other is field control. So we shall solve the armature control problem in its entirety and show you how to obtain the transfer function. of the applied armature voltage, that is the input to the speed or the position of the shaft of the motor. And we shall leave as exercise for you to derive a similar transfer function for field control. Okay, down the line we shall see how these two modes differ. So thank you very much. With that, we've come to the end of this particular module.